Hello and welcome to Paper Boys, the podcast where we unravel the research papers behind the latest major headlines in science. My name is Charlie. I'm here with my co-host James.
Happy to be here, Charlie. Happy to be here.
Good. You're contractually obligated, so...
I have no choice in the matter.
Yes.
For those of you just joining us, do you ever hear about science in the news and wonder, isn't there more to the story? Isn't there more to the actual research than the science headlines give away? Well, every Thursday, Charlie and I dive into the actual research papers behind these headline science news to open up these beautiful new discoveries and give them the detail of discussion that they deserve.
Yes, we do our best to do them justice, and I will say that today I'm going to do my best, but I don't know that I'll do this paper much justice.
Okay. Hey, all we ask is that you leave a little blood on the floor and give it your best shot. Leave some blood and tears and sweat behind.
There's a lot of tears on this one, but...
All right. Well, so tell us, what is this paper about?
So this one is about a new technique that these scientists have developed and also used on data to determine the Hubble constant, which tells us how fast the universe is expanding.
Is this a constant like the same way the permittivity of free space is a universal constant?
It is, but let's not dive into that rabbit hole yet, because it actually, They call it a constant, but it actually changes throughout time.
That's not a constant.
So it's really, I think, called the Hubble parameter, but the Hubble constant specifically refers to the value that it has at this time in the universe's history.
Whoa. Okay. That sounds trippy.
There's too much to unpack in this paper, man. First, we need to get to what is the Hubble constant, what is expansion. So,
before we get there,
yeah,
if you haven't listened to the show before, why are Charlie and I qualified to even talk about this? Well, we are both.
In this case, it turns out I may not be qualified, but but please keep listening.
Please keep listening. You're qualified. So Charlie and I are both PhD students who read lots of papers for our own research. This podcast is our way of sharing our love for science with anyone who wants to learn more about discoveries that affect us all.
In short, we are the Paper Boys.
All right, Charlie, before we get into this ravishing Hubble constant parameter that you intrigued us with earlier on, we just want to say thank you to everyone who's listening. If you are not already, please do follow us on Instagram or Twitter. Our handle is @PaperBoysPod. You could even follow us on both. That's possible.
Yeah, only if you're a super fan, though.
Yeah.
Speaking of super fans, check out our Patreon. Patreon.com/paperboyspod. We have a lot of great rewards on there. The lowest tier you can get already gets you a bonus episode every month. And this month we covered relativity and a really cool experiment from the year 1919.
Really cool.
They literally trekked into the jungle in Brazil and some island off of Africa, and they measured a total eclipse, and they published a picture and proved relativity correct. And anyway, don't want to spoil it.
Yeah.
You just got to check out the bonus episode. Patreon.com/paperboyspod.
Okay, Charlie. So what got you turned on to this Hubble constant in the first place? Imagine you saw it in the news somewhere. Because that's how we find every article.
That is, yeah. Big surprise. No, this was actually one where I actually didn't really have a good topic for this week. Actually, man, I went through a bunch of interesting topics. There was a really cool paper this week about how Minecraft... Ooh. They had participants play Minecraft, and it's increased their creative juices basically. But the paper was totally closed access, and I couldn't get access to it.
Really?
But I was really bummed because I wanted to cover that one because we've actually had one of our Twitter followers, Lucas, suggested video games as a paper topic, and this was the perfect time. But anyway, sorry, Lucas.
Dang.
You'll have to check it out next time when we get a chance.
We'll have to unlock it.
Yeah. Anyway, so I was browsing around trying to find a cool science topic, and I just came across these headlines. One of them was from phys.org, new method may resolve difficulty in measuring universe's expansion.
Okay. Mm-hmm.
So we got a little bit of a hint of what's going on here. CNET says fierce neutron star collision shows how fast the universe is expanding.
Dude, this is like the perfect follow-up episode for our bonus one. Because when we started talking about the universe expanding because like, the Einstein redshift.
Yeah, I've got a cool little Einstein anecdote for this paper as well.
The best.
Yeah, once we start talking about the Hubble constant. And then, I saw another headline from Science Alert. Neutron star smash-up just provided a new measure of a fundamental cosmic feature.
Is this like a new Beyonce-Rihanna smash-up with the Hubble constant?
It is, yeah. When these two neutron stars came together, it was collaboration of the century.
It was art from the moment they got together.
It was, yeah.
I can't wait.
Moment is an accurate description. Like the timescale on which they're measuring these gravitational waves that are given off by these neutron stars colliding, it's like seconds.
Really?
Yeah.
I mean, this is like real time. They're like, oh my God, like two stars just collided, minus the however many thousands of years.
Million years. But
yeah.
But yeah, I mean, the actual process of them colliding takes they slowly close in on each other over a very long time.
But like you blink and you miss two neutron stars colliding.
Yeah, exactly. Yeah, so that's all the news articles.
Okay.
And they misled me into thinking that I'd be able to understand this topic.
As an actual rocket scientist, that's a bold statement, Charlie.
Yeah, this is like
when
this stuff is like rocket science to rocket scientists.
It's like when you get in the rabbit hole and you're at like the rabbit hole conference and then you realize like there are, I guess, just more rabbit holes.
A lot of rabbits out there.
There are a lot of rabbits.
Yeah.
You're just one of many. What was the actual paper then that all of these news articles were about?
So the actual paper, this was published in Nature Astronomy on July 8th, 2019, just a few days ago.
Wow.
It's called A Hubble Constant Measurement from Superluminal Motion of the Jet in GW 170817.
All right. I'm going to need you to break that down for us.
Yeah, I feel like all those numbers and letters at the end confused it, but it's Hubble constant measurement.
Hubble constant, like you mentioned before, the rate of expansion of the universe.
Yeah, and from superluminal motion, so faster than light.
Hold on.
I know.
Hold on.
I know.
This just got crazy.
Got pretty wild.
In a hustle.
Uh-huh. And then it's superluminal motion of the jet in GW 170817. So that acronym is
star.
It's an observed neutron star merging event.
Okay.
Or like a region where that happened.
So these are two stars merging together. The event is called GW 170817.
Yeah, I think that's just the date of the observation.
Oh.
August 17th, 2017.
That makes sense. Okay.
So there's this jet of matter being ejected from that
Whoa.
region. And so they're measuring this superluminal motion of that jet in order to determine the Hubble constant.
Is that kind of like the what is the galaxy? Is it M87 that has the big streak of light coming out of it where I think there's a black hole?
Yeah, so these like jets of matter are common to be emitted from like a black hole or these stars colliding.
Oh man,
basically like places where there's lots of energy and mass in one place, like stuff shoots out. So
whoa, I'm looking at a picture of M87 right now, which is just so cool. Not related to this at all, but just an awesome picture.
Okay, that does not even look real.
It doesn't look real, but it is.
That's wild.
From the Hubble Space Telescope. Not related to the Hubble constant.
Named for the same person, Edwin Hubble.
Okay.
But
I digress.
So this paper was by, the first author is Kenton Hotokazaka from the Department of Astrophysical Sciences at Princeton University. And then there were several other authors from Tel Aviv, the Netherlands, Caltech, and Australia.
Oh, Australia.
Yeah.
Not to offend any of our Australian
Caltech.
Oh, yeah.
What if people did that, like when you just talked about any old place, like try to copy their accent?
Oh, University of Iowa. Oh. Okay. Okay. All right. So, I mean, I feel like we've just walked up to the edge of a cliff.
Yeah, pretty
much.
Like
I'm a little nervous.
Listeners, just
palms getting a little sweaty.
Now.
This is the point of no return. If you enjoyed the episode so far, you can.
Yeah, what is it? Is it from like Dante's Inferno? Like, abandon all hope, ye who enter here.
Yeah, I don't know which ring of hell the Hubble constant lies on. But
yeah.
Or paradise if you're into this. Yeah. So join us.
Yeah.
Join us. So, Charlie, biggest question. Well, there are a lot of questions. You said superluminal. And then you said that that's faster than the speed of light. I'll have questions about that later.
Yeah. Let's
But
start
first off,
basic.
Hubble constant.
Yes.
What
What's
is
the
it?
deal with the Hubble constant?
Special guest Jerry Seinfeld comes in to explain astrophysics this week.
Yeah, so the Hubble constant. Basically, I think most people are probably familiar with this concept that the universe is expanding.
Yeah. Which is weird that people are used to that because it's like...
Because that's not always been known.
No, in my daily life, I have zero evidence that the universe is expanding.
Oh, well, yeah, obviously. But so that's something that we'd like know from, science class and textbooks and stuff. But how do we know that? It's when we look out at really distant galaxies, we actually can observe that they are moving away from us. And they're all moving away from us.
Do you have to make this measurement like over time? Like you look at it one day and then you look at it the next and then...
No. So, and here's another term people are probably familiar with is redshift.
Mm-hmm.
So what that essentially means is when you're observing some galaxy, you sort of expect it to have a certain distribution of light coming at you that you can measure. And then based on what you think the distribution should be, and then based on what you actually measure, that light gets shifted towards the red end of the spectrum, meaning longer wavelengths. And that's because of the Doppler effect.
Okay. The waves are traveling away from you. So as you measure it, it's like the wave's actually expanding.
Yeah, the wave is sort of like stretched out because the galaxy is actually moving away. It's the same way that like if a truck drives by you and it's like honking its horn.
Like NASCAR or Formula One.
Yeah.
Or
the
horns or sirens.
Yeah, like when it's going away, the pitch of the sound actually gets lower. Like the like the low pitch is because it's moving away. So it's stretching out the wavelength of the sound.
Cool. So sound and light for galaxies. So it's moving away, you get some red shift.
Yes, and that's the Doppler effect. And so the red shift actually tells you how fast that galaxy is moving away from you.
Okay.
And what we find is that the further away a galaxy is, the faster away from us it's moving.
Whoa. So it's not constant.
No. That's what's crazy, is that it's like accelerating.
Wow.
Yeah. So, and it turns out that relationship between the distance a galaxy is from us and the velocity it's moving away from us follows a linear relationship.
So the distance away that a galaxy is...
So let's say we observe one galaxy. It's moving away from us at some speed. And then we see another galaxy that's twice as far away. It's moving twice as fast as the first one.
Wow. Okay.
Yeah. And it's, so it's this linear relationship, and that line has a slope.
Okay. And
so
that slope is the acceleration?
That slope is the Hubble constant.
What?
So it's literally that the velocity we observe equals the Hubble constant times the distance away.
Okay.
Does that make sense? Like, like y equals mx plus b, forget about the plus b part.
The m is Hubble constant.
M is the Hubble constant. Yeah. That sets that slope.
Okay. What units are the Hubble constant in?
It is in kilometers per second per megaparsec.
Okay. What is a parsec to our...
A parsec, I think,
listeners?
Is like 3.6 light years.
Why don't they just use light years? And did Star Wars invent the parsec? And then it was adopted into popular scientific thought.
No. Parsecs are a real thing in astrophysics. So it's one parsec is 3.26 light years. 1 megaparsec is a million parsecs is 3.26 million light years.
All right. I'm going to fight the urge. I'm going to fight the urge to talk about that more and just accept the fact that it's 3.62 light years.
So like a typical value that we have calculated for the Hubble constant is something like 70 kilometers per second per megaparsec. That means that for every 3.2 million light years away that a galaxy is, like each additional 3.2 million light years away, it has accelerated by 70 kilometers per second.
Wow. So, I mean, like these galaxies are moving away at like 40 miles per second, basically.
Oh, faster than that. I mean, the actual value of the velocity that they have is like thousands of kilometers per second.
Oh, that's just their acceleration.
Really
just
far
acceleration.
away.
Yeah.
Yeah, these things are really far away.
Wow. Okay.
So do you want to hear the Einstein anecdote?
Yeah.
So
of course.
When Einstein developed his equations, like describing the cosmology of our universe, he had to include this parameter that he called the cosmological constant. And he included it in one of these terms because it was in order to correct for an expanding universe, essentially. Like, he was observing that without that constant there, the solutions to his equations showed that the universe was expanding. And he was like, well, that's obviously not true. The universe is fixed. So he just put in like a dummy number to say, we have to include this dummy number in order to make it work as we think it should.
Whoa. So his equation showed an expanding universe, and he didn't believe it. So he
didn't
invented
believe
this
it.
constant.
So he invented a fake number. And so I guess this guy in 1922, Alexander Friedman, used like the relativity equations to theorize this expanding universe. And then George Lemaitre independently theorized it and came up with like an initial number for the Hubble constant in 1927. And then Edwin Hubble came along like around that same time. He proved the theory that it was expanding, and he came up with a really accurate number for the Hubble constant, which is why it's now named after him.
Whoa.
But so Einstein, after Hubble proved that the universe was expanding, Einstein like famously said that the cosmological constant was his biggest blunder of his entire career.
Really?
Yeah. Isn't that crazy?
That's nuts.
I mean, think about it, dude. Einstein had the answer right in front of him. He could have been known for also proving the universe was expanding.
Yeah, he would have been that guy.
Yeah. He would have been not only been Einstein, but he also would have been Hubble. You know, we'd be calling this the Einstein constant today.
I think doesn't he already have a constant?
Oh, I'm sure he's got like 1,000.
Yeah.
But I mean, this is a big one, you know, like this is like this shapes how we understand the universe, you know, like in every way.
Yeah.
In much the same way that relativity does.
That is so cool. Poor Einstein, man. Poor Einstein.
Guy, you know, he's like the Van Gogh of scientists.
If only he was just a little bit smarter, you know?
He could have had so much more.
Could have had so much more. Okay, that's fascinating. So that's how Hubble rose to fame.
Yeah, I mean, among other things. So do we understand the Hubble constant and like what it means and that the universe is expanding enough to move on?
Yeah, I mean, questions beget questions.
Okay.
So I'm ready to ask new questions.
Okay, shoot.
How do you measure this? And how accurately do we know it?
So that is kind of why this paper that we're going to talk about is important.
Okay.
Because we know it very accurately from two different techniques of measuring it, but they don't agree with each other.
Dun, dun, dun. It's like if you listen to our bonus episode, you would have seen this movie before.
Yes. Yeah, it's exactly like that. Like you need to go find a new way to prove this and just figure out which one is wrong, you know?
Yeah. This obviously referring to the precession of Mercury.
Yes,
orbiting
exactly.
the sun during eclipses.
Yeah.
But
James, don't give it away. They got to go listen to the episode.
I mean, we say it in the episode description.
So, you know, it's a simple curve. It's a simple curve. It's a line. So all you need is a distance and a velocity, and then like a lot of data points to measure this line.
Can't we do that with every... I look up at the sky. There are a lot of objects up there that we can measure.
Yeah. And I mean, also like in theory, you can measure it with just 2 data points because it's literally just like velocity over distance gives you the Hubble constant. So if you can make a measurement of an object's velocity and of its distance very accurately, then you've got a good measure of the Hubble constant.
But the very accurately parts are probably hard.
Yes, that is the crux.
Okay.
So there's sort of like a couple ways that they've measured this historically. The one that I kind of understand how they do is, so I mentioned how they get the velocity. That's the redshift part. So they can, you know, look at the way the light has changed and get a velocity data point for that. But then it's very hard to measure distances when you're looking out at the night sky.
Yeah.
Like
I can see that.
How would you know the difference between a giant star that's really far away and a small star that's really close to you?
You could, I mean, I guess you look at how it changes as the Earth rotates. That doesn't quite make sense.
No, the Earth doesn't move nearly enough to get measurements like that.
How do you do
when
it?
we're talking about stuff that's millions of light years away. Maybe billions, you know?
Yeah, I have no idea.
So they kind of have to like make some assumptions. One thing that they do is called I just learned about this, called the cosmological distance ladder. It's pretty cool. Like I'm going to butcher this explanation, but I think they just like have a way of sort of knowing distances to certain objects and like the way that they should appear in certain types of measurements that they can do. And so then they can like relate them to each other. And so they can back out like some bound on what the distance actually is just based on like the way the measurements look.
So, I mean, it's like you
Terrible
sort of have this like shoddy makeshift ruler where you're like, we know how far this is. And then you're like, okay, let's see how many of these rulers it takes to get to like
Yeah.
Sagittarius and then whatever.
I think that's...
Sagittarius being a horrible example.
But if any like astronomer is listening right now, they're probably cringing. But yes, I think that's how it kind of works.
And by shoddy, I don't mean shoddy, obviously.
But I think it is kind of shoddy. Like that's why
hard.
they don't have a very accurate, or that's why like they're struggling to get agreeing answers on this.
Yeah.
Because
It's
there's like
challenging.
intrinsic errors in these methods, you know?
Yeah.
So that's one way of getting distance. There's another one, and I think this might even be like part of the distance ladder thing, but this is just what I'm sort of familiar with, is they have standard candles, they call them. And
How many candles to a parsec?
so one example of like a standard candle, basically what that means is it's an object in the night sky of a known brightness. They know the absolute brightness of the event.
Mm-hmm.
And so then by measuring its apparent brightness, they know how far away it is just from like pretty simple math. So like one example of that is like, I think type 1A supernovas. I don't really know what type 1A means. That's just what they say. I guess have a very like specific way that they're meant to explode and like a very specific amount of like energy or brightness that they have. So when you observe one of these supernovas, you can figure out how far away it actually is.
Oh, okay.
And those happen in galaxies. So you get the redshift of the galaxy and you get the distance from the supernova, the type 1A supernova. And then boom, you've got your Hubble constant.
Okay. That's something you got to read up more on. It's interesting. It's got to be really, it's
Man,
really
it's
hard.
so interesting.
Just to clarify too, I just looked it up. A type 1A supernova is a type of supernova that occurs in a binary system in which one of the stars is a white dwarf. That's the only requirement, I think. So
I think, yeah, just like based on the physics of how that works,
cool. Okay.
they all happen at the same brightness.
Interesting.
So those are some ways that they get these distance measurements. But I gather that the problem is that those depend on like some of these physical assumptions and also like a specific cosmological model that sort of like would give you a certain expected expansion. So this new technique tries to like get away from those assumptions and try and get something that's more absolute.
Okay. How does it do that?
So now, so we haven't even actually gotten into the paper yet. That's all background.
What? Okay.
So I will say, like, researching this was really freaking hard. I literally, within the first sentence of this paper, I had to look up 3 different Wikipedia articles.
That's awesome. I mean,
Yeah.
deep dive.
I learned a lot, and like it kind of made me want to switch my degree because this stuff is really freaking cool.
It is super cool, I bet. Yeah. Says the guy who's literally studying astrophysics.
No, I'm not.
I know you're not, but like,
No, astrophysics has a pretty specific meaning, and I'm definitely not studying it.
I
So
mean, you're studying space physics.
no, I'm not. I'm studying plasma physics.
Yeah. Well, you're the one who's like 99% of the universe is made up of plasma anyways.
Oh, that's true. Yeah, the study of plasma is the study of the universe.
I'm just saying, it's just funny that like,
No, this stuff is really cool.
no, it's also very different. I'm not trying to take away from that.
And the reason why I'm saying this is to act as a buffer because we're about to dive into like more stuff. So
Hedging
I'm
your
trying to
bet.
give some time to like let people digest what they just learned
Okay.
because we're about to dive into new stuff.
All right. So we got the Hubble constant. Just a quick recap.
Mm-hmm.
It's based on measuring the distance and velocity of bodies in the universe, which it turns out is very hard to do.
Yes.
And this is a new method.
Yes. So with this paper, they took these observations of this pair of neutron stars that merged.
Mm-hmm.
And I guess when these neutron stars merge, they're orbiting each other and they're very dense, like very, very massive. Like they're only, maybe like 100 kilometers across, but
Whoa.
each of them weighs more than our sun.
This is like a teaspoon of this stuff weighs like 2,000 tons.
Yeah. Yeah. You always hear those things, or they'll show like, a neutron star projected over like Manhattan. It's like the size of Manhattan, but it weighs more than our sun.
Whoa. Okay.
So just to give like some, perspective. So these two neutron stars orbit each other, and because they're so massive and they get really close, like they orbit each other, hundreds, thousands of times a second in the last few moments before they collide.
Whoa. Okay.
And this literally like causes ripples in space-time.
Okay, this is like with LIGO then, where
Yes.
they're measuring the gravity waves?
Yes, exactly. So LIGO, and I think there's another one that now we're able to get these very like good, precise measurements of gravitational waves, which is like a pretty new thing that we are able to do.
Interesting. Okay.
Yeah, so I kind of skipped it, but when they make these ripples in space-time, those are gravitational waves. And so we can measure the signal that is produced by these neutron stars merging.
It's so crazy. I mean, I remember reading about LIGO, and it's like you dig these huge tunnels underground that are miles long, and then you isolate them from every single possible source of noise, like
Yeah.
small seismic activity and highways and stuff like that. And then you just get the faintest little measurement of this gravity wave.
Yeah, but it's
so
cool because now that we have these instruments, like we can start detecting these events. And apparently they happen pretty frequently. Like they expect these to happen at a rate of like 3 per year.
Whoa.
Yeah.
Nice. Dude, just switch your PhD.
I know, man. That's what I'm saying. I want to switch fields.
And they have one in Washington, one of the tunnels.
Really?
Yeah. Washington State.
Maybe I'll just go live down there.
Yeah.
Sounds fun.
So stars are orbiting around each other, getting gravitational waves. They're orbiting really fast. Does this give them some new method then for trying to get the Hubble constant?
Yeah. So it does. I'm going to try and figure it out on the fly exactly how this works. So they reference this actually like pretty old paper from 1986 that sort of explains this technique. And honestly, I didn't understand this new paper until I read the old paper. And this is pretty cool. Like this guy Schutz, published in Nature, it's like a 2-page paper, just talks about like using this technique where if you make a measurement of gravitational waves from these neutron stars merging, and then if you have like very large interferometers, so in the new study they actually like got measurements and imaging of this region of the sky where the event happened using it's called like very long baseline interferometry, which is the same way that they took the image of the black hole.
Nice. Which we have an episode on. Small paper voice plug.
Yeah. So if you want some background on that interferometry technique, go check out our black hole episode. Anyway, so
Cool.
they get these gravitational wave measurements, interferometry measurements, and then they also just measure like the electromagnetic radiation that comes off of them.
Okay. And yeah, that's like terahertz radio imaging for the VLBI.
I guess so, yeah. Yeah. So I guess what you can do is like once you measure that gravitational wave, now you have the frequency at which they orbited each other in those last moments.
Mm-hmm.
And based on the way that they look, you can make some assumptions about their mass. And so if you know the frequency and the mass, you can actually calculate the angular momentum of the system.
Okay.
And then once you know the angular momentum of the system, then when you measure these electromagnetic waves, this is just like so you measure the electromagnetic waves, and I guess ones that are being emitted along the axis of rotation are circularly polarized, which, James, you know what that means.
It just means so in an electromagnetic wave, you have an electric field component and a magnetic field component. It means they're rotating around an axis.
Yeah.
So it's like, it's not just vertical for the electric field and horizontal for the magnetic field. Like those are constantly rotating in space. So like spacecraft use circularly polarized radio waves.
Okay. I regret asking because now we've gotten so far from the original.
But so
the point is,
if it's emitted along this axis, you can look at the polarization and figure out where it's something about its origin.
yes. So because the electromagnetic waves emitted along the axis of rotation is circularly polarized.
Okay.
The waves emitted like perpendicular to that, like flying out from, like as if the stars are like throwing it off to the side, is linearly polarized. So when you measure the radiation here at Earth, there's some percentage of it that's circularly polarized and some that is linearly.
Cool. So like depending on, you could use an antenna if you use a circularly polarized antenna, you'll get a stronger signal.
Yeah.
If it's coming from whatever
And basically, yeah, like that percentage tells us the orientation of these neutron stars relative to us. Because if you had like all circularly polarized radiation, then you know that we're looking like straight down on this thing.
Okay.
We're looking like at the plane of the rotation of these two stars.
Wow.
If we had all linear polarization, it'd be like looking at, it'd be like looking at like a flat disk of them, like, and they're spinning around each other. Like looking at the rings of Saturn, like,
totally horizontal.
Flat on, yeah.
So like they're spinning, but like you sort of just see.
Yeah.
Okay. That makes sense.
So I guess when you know the angular momentum and you know the orientation of the axis of their orbit relative to us, I guess for some reason that gives you a very accurate measure of the distance to that event. And that's just math. Like that's just math and like, astrophysics stuff that like it'll get more confusing if I try to explain and I don't understand it, but
so there are these two parameters that you can measure from these observations that give you a much more accurate sense of how far away these stars are. But I imagine it's probably non-trivial to measure these parameters.
No, I mean, like you said, you have to build these underground tunnels and these measuring gravitational waves is something we've only very recently been able to do with like reliability.
And that's why this paper is so novel.
Right, that's why this technique is novel. Because now we have these interferometers, which literally take up like the globe. I mean, you need stations that exist thousands of kilometers apart from each other in order to do that technique.
Yeah, on different continents.
Yeah.
With like terabytes of data and all that. It's hard.
All the timing. Yeah. And then the other aspect is the measuring the gravitational waves, also a new technique. So when you combine these two things, you can get a very, very accurate measure of the distance to the object.
Wow.
This author Schutz says to within 3%.
Wow. And this guy was predicting it in 86.
Yeah, I mean, not even so much predicting, just like saying, like, I mean, theoretically, if you have all this data, you can do this. And he was saying, like, people will be doing this because currently they're constructing these very long baseline interferometers.
That's so cool, though. I mean, that was, 33 years ago. And he's like, I mean, I guess if they're constructing it, you don't start constructing it if there's no path forward or no utility. But
it's cool that we get to live in the time when we're doing it. And he had to just like talk about in the future. But it's cool. Like, I mean, this guy seems like he was a big shot. He's referencing like one of his citations is Kip Thorne, personal communication.
Oh,
and like, man, this guy's just like a friend of Kip Thorne's.
Humble brag in the citations.
Such a humble brag. I know.
That's when you're like a bigwig scientist. You're like humble bragging in your references.
Yeah, like name dropping.
Yeah.
It's just really cool. So then once you have the very accurate distance, what you do is, because you've measured this radiation at different radars around the world, you can actually triangulate the position in the sky.
Oh.
Like of where the source is.
Okay.
So they use like basically the different measurements at different stations, and they figure out the very small time delay of like only a couple of milliseconds to figure out, all right, it's like when the cops track someone on a TV show, like you take 3 cell towers, figure out the time delay, and then boom, you got your perp.
It's like cereal.
Yeah. So they find the perp up in the sky, and I guess they
can. You know how fast you were going?
So yeah, you were going superluminal speed.
Yeah, we haven't even touched on superluminal. Oh my god.
Yeah. Actually, we still haven't even gotten to the paper that this episode is about. So
okay.
Anyway, so after you triangulated the position in the sky, you kind of have like some sort of like error box where you're like, I'm certain that it's within this box.
Uh-huh.
And what you do is you just measure the redshift of all the galaxies in that box.
Okay.
I wish we had video because everyone could see me like talking with my hands really aggressively.
We will have video soon.
Soon.
So
what you do is you measure the redshift of all the galaxies in that box.
Okay.
And then because you know the distance very accurately to the actual true galaxy that this came from, you just use that distance and the velocity measurement from all the galaxies, and you plot like a distribution of Hubble constants.
Okay.
And then most of them are total bogus, because most of them you're going to get a velocity that does not correspond to that distance.
Yeah.
One of them will jump out as a value that looks right, basically.
Okay. That's close to what you expect and within your error.
We know that, the number can absolutely not be higher than 120 or something. Like that's the figure that he gives in the paper. And we know that it's going to be somewhere around like 60 or 70, maybe 80. Like, so you're going to plot a distribution. There's going to be a bunch of ones that are like 302 and like 89 and like just, kind of weird numbers. But there will be one that looks right. And so you can kind of say with reasonable certainty that is where the gravitational waves originated. And that's our value for the Hubble constant. But the real goal would be to do this measurement many times over like many different gravitational wave events. And then you put all the data points on a single distribute. Like, let's say you get 30 data points from that one observation and one of them is correct. If you do this like 10 times, now you've got 300 data points and 10 of them are correct. And so it becomes much more obvious and you can get a much tighter error on that.
Wow. And it sounds like this might actually be feasible given the frequency of these events. Like they happen pretty often.
Yeah, that's what Schutz says. He's like, based on the frequency, this could be like a 1 to 10 year time scale thing.
Wow.
Where we finally have an answer.
That's so cool.
Yeah, it's really, really cool. So that's the technique that they do in this paper, basically.
So what is the paper?
So the paper is like they look at this specific event that happened, GW 170817.
Oh, okay.
Which was really cool, by the way. It has its own Wikipedia page. It says the discovery and subsequent observations of it were given the Breakthrough of the Year award for 2017 by the journal Science, which is pretty freaking cool.
Yeah.
So like this was an important event, Anyway, what they do in this paper is there's this jet of matter being ejected after these two neutron stars merge. And we observed that jet. We also observed the gravitational waves from the event.
Okay.
The jet is superluminal.
How?
So it's not actually traveling faster than light, but this matter is being ejected at very close to the speed of light.
Constants are changing. Light's going faster than light, but not going faster than light. What is this universe,
Literally,
man?
like the universe doesn't work the way that I thought it did.
Yeah. Wait, but so, okay, hold on. So it's not actually going faster than light, but it's been ejected. And what?
No. So I think at this time we need like another buffer. Maybe we'll just play like some Jeopardy music or something.
Cool jazz.
Just like let people digest the Schutz paper from 1986. Like, how did we do this, before we start talking about superluminal jets, because we've already changed pace, so many times.
Let's we need like a good Star Wars, some sort of movie. Oh, I got it. Here we go.
You've never heard of the Millennium Falcon?
Should I have?
It's a ship that made the Kessel run in less than 12 parsecs.
Yeah, so now we know what parsecs are. We realize how ridiculous that statement is, right?
Yeah.
It's a distance. You can't say it went faster than 12 parsecs.
Yeah, that is pretty funny.
Yeah. Anyway, I feel like that's one of those things that everyone says is like a trivia from Star Wars. Like, actually, parsecs are as a unit of distance. but it actually is.
But it sounds like seconds.
Yeah. Anyway, all right. That was a good buffer. Thank you, James.
No problem.
So, you want to hear about superluminal jets now? Now that we're already pushing like the longest episode of Paper
It's just making me question everything now. But
no. If once we talk about it, it'll make sense.
Okay.
Probably not. But so it's this jet is essentially just matter that's being ejected at a speed very close to the speed of light, and the jet is being ejected in our direction. So like it's kind of headed towards us, and so I guess what happens is like the material. Like, as it's being ejected, it's also emitting light at us. And the light obviously can't travel faster than the speed of light. But so, think of it like a shock wave.
Yeah.
Like, as like a jet is approaching like the speed of sound and that air is getting pushed, like all of the sound ends up reaching you kind of at the same time, giving sort of the impression that it's like moving very fast. So what's happening is that the light, like as this train of matter is moving, it's emitting light and it's like almost catching up to the light that it emitted, a couple minutes ago because it's almost moving as fast.
Yeah.
But it's also emitting light once it's caught up. So like
it's like the extreme blue shift, right? Because
I don't know if that's really how it looks superluminal. It's really because then when all the light finally gets to us, it kind of all gets here almost at the same time.
Really? So there are like weird effects from it?
Yeah, because all the light kind of gets bunched up from the whole jet like moving. So it gives the appearance
In contrast to like most things that we observe where it's like the matter is relatively stationary to the light that it's giving off.
Right. So you can make like reasonable measures of its velocity.
Weird.
But because it's moving close to the speed of light, it like all the light kind of bunches up, gets to us at almost the same time, and gives the appearance that the jet itself has moved faster than the speed of light when it actually hasn't.
Okay. Interesting.
But so they call these superluminal jets, and they used this very long baseline interferometry imaging of this superluminal jet that came after this neutron star event to figure out that orientation that we were talking about. So remember how I said that it was very important, like how the orbits of these stars is oriented relative to us?
Yes.
Because you use that to calculate like the angular momentum, which gives you the accurate measure of distance.
Mm-hmm.
So they use imaging of that jet to get the angle. That's kind of like the new technique that they're using in this paper.
Okay. And so they actually got to use that then?
Yeah, so they did that, and they had like a formula that they calculated for the distance to this galaxy where it happened as a function of the angle that they're trying to figure out. And so like based on the measurements, they kind of found like a distribution of like potential angles, and they kind of used like different techniques. Like they did some analytic modeling, they did some Monte Carlo simulations of like totally like simulated jets, you know, like they ran like a computer model of what the jet could be like, and they sort of matched it up to the data.
Cool.
That's like such a bad explanation, but
no, I mean, that was good. That was a good explanation of a very dense paper.
Yeah, well, so then where they come out with an actual Hubble constant in the end, you can see this figure 2 here. They show like a distribution of potential Hubble constants, like what we talked about before. You can see that they have like one distribution, which is given, let's say you only had the gravitational wave data.
Mm-hmm.
And it's like kind of a pretty wide spread. Like you can't really get a very good accuracy.
Yeah.
And then they have
sort of like a skewed.
Yeah,
it's not a Gaussian.
Skewed,
it's like
it's pretty
skewed
wide
out to the right.
Yeah. And so this other distribution here, it's like very narrow, and it's very obvious like where the center of it is.
Mm-hmm.
And that is when you combine the gravitational wave data, the very long baseline interferometry, and this Monte Carlo analytic modeling that they did.
Yeah, that's much narrower. Looks like a Gaussian, very clear, mean.
Yeah, and the value that it predicts actually falls within the range that we expect the Hubble constant to be.
Right in that.
And that's pretty important.
60 to 70 kilometers per second per megaparsec range.
Yeah. So the actual number that they finally come out with is 70.3 plus minus about 5, whereas the previous best estimate was 74 plus minus 16 and 8. So like,
wow.
So that was like a pretty wide range, whereas now we've got like a plus minus 5. And most importantly, they do like a quick calculation and say that if we do this 15 more times with 15 more neutron star merging events, provided that the data is good enough, we can get a measure of the Hubble constant with a precision of like 1.8%.
Wow. So like if you look at plus minus 5 out of 70, it's like 7% error.
Right.
So that's impressive.
Yeah. So if they bring this down to
more measurements.
1.8%, then that will be like well within either one of the two measurements that right now have like a discrepancy. Remember how I mentioned that at the beginning?
Yeah.
So hopefully like getting this new measurement will draw us to one or the other and tell us which one's wrong.
Okay, cool.
Or maybe that they're both wrong.
Ooh. I mean, that's pretty cool. These authors are going to get a lot of citations.
Yes. This is going to be like, this one's going to be, I think, have a really big impact in the astrophysics world.
No, that's awesome. Were there any other big significant findings you think from this? I mean, I think that's already pretty big to like take this new technique and apply it to a star and show that it like already helps a lot in reducing the error of our estimate of the Hubble constant. That's already pretty good. Yeah.
I mean, like this was like a 3.5-page paper. It was
which is crazy,
freaking slog the whole way through. But yeah, I mean, it's very focused on just like the actual like analysis of this data, and it doesn't really talk about all this theory. The theory I kind of had to find elsewhere. Wow. There was a couple just like little miscellaneous things that were really freaking cool. Like I learned probably my new favorite science term.
What's that?
Circumnuclear megamasers.
Holy cow.
Isn't that just like a
Megamaser.
cool word?
I'm just imagining cats with megamasers shining from their eyes.
Yeah.
What does it mean? Lol.
It's the name of a metal band that the authors are a big fan of.
Nice.
No, it's a megamaser is a type of astrophysical maser, which is a naturally occurring source of stimulated spectral line emission. It's basically just like a giant source of light.
Okay.
But the circumnuclear megamaser, and that's like a real word that they use in this.
Wow. That's when you know you've made it, man. When you get to use words like that.
Unironically, I mean, come on, what a cool field.
Yeah.
It's also this paper that we're talking about is now referenced on the Wikipedia page about Hubble's law.
Ooh.
It's like talking about like techniques, and then like the last paragraph is now like, in July of 2019, scientists proved that it's possible to use gravitational waves and very long baseline interferometry.
It's probably the authors who threw that into it.
Went and
We should
edited it,
track the IP.
No one's deleted it yet.
Yeah. No, that's actually really cool.
I think, that's a very like millennial way of signifying the significance of something, but it kind of is like that signifies like this is important enough to be a line in a textbook of like how we do these things,
Yeah. Also, just we literally bring it up, I think, on every episode, but it's like 5 years of work, probably a couple, I think it was 5 years, I don't know, years of work, building off the work in 1986 and how many students got degrees from this, and you get a line on Wikipedia.
Yeah.
I mean, and a Nature paper and the advancement of science, but like,
Yeah.
that line on Wikipedia is going to outlive any of us.
Yeah. I mean, like that's the culmination kind of. It's not really. I mean, the culmination is like the knowledge and it was the journey.
Yeah, it's the journey. But at the same time, it's like, I was thinking about this a lot. I had to TA a writing class, and you're trying to convince students why writing is important. And you're like, truthfully, that's pretty much all many scholars leave behind, writing.
Yeah. It's literally, I mean, it's the only way like you can be,
Doesn't
look at,
matter
like,
what circuit you build or...
it's like compare like Tesla to Edison,
Yeah.
Edison, in this analogy, he's the good writer.
Yeah.
And he had a way bigger impact, But Tesla was a smart guy, but couldn't communicate his stuff,
Edison also left us light bulbs.
Yeah. Yeah.
Oh, on top of writing.
Yeah,
and
no,
patents and
that's what I'm.
designs.
Yeah, that's what I'm saying. Is like it's the ability to communicate and sell your science
Oh, yeah.
that
Yeah.
is equally as important to just being a smart person who can figure stuff out.
It's not enough to just be
Like
smart.
there's lots of people throughout history who like came up with stuff and it was in their margin notes, but then someone later on the line gets credited because they published it correctly. And
There are also a lot of people who are not very smart who've been very successful.
yes, you're listening
So.
to two of them, minus the success.
Yes. Well, was there anything else you wanted to add about the paper?
Not about the paper. I will say this is one of these cases where the news articles were instrumental in understanding this paper.
Really?
Yeah. Like I had to go back and read the news articles, re-understand what was even going on, then dive back into the paper and be like, "Oh, okay. I think this is where they're talking about that."
One of those papers where it's like kind of swimming in open water and you just get like sucked under by a wave and then
Yes.
you gasp for a quick breath of air before the next wave of circumnuclear masers hits you and
Yeah.
then
Pretty much like
get a breath of Wikipedia.
yeah, basically like I couldn't really read this paper in like a linear fashion because I went so often to like another source to try to understand what was going on and then reread and then skip ahead, and then this paper was hard. Like normally I come to the end of these and I think, hey, the lesson of Paper Boys is that you, the listener, should go read these papers for yourself because anyone can do it. This is one of those papers where that is just not the case.
You just need a lot of discipline knowledge.
You need a lot of schooling, yeah.
Yeah.
And I think that's just the way that this paper was written. It was written for a very technical audience, assuming a standard like shared language, basically.
3.5 pages. It's like
yeah. Whereas like
every
a lot of
word
papers,
counts.
yeah, like a lot of papers, they'll really explain theory and they'll kind of boil it down, and then they'll throw the really technical stuff later down the line.
Yeah.
But this one didn't mince words. It was just like, you have to be a Princeton astrophysicist or at that level to like just get it.
To fully get it. Although I will say You don't have to get everything to get the gist out of it. Like
No.
shouldn't.
But this is one where you can get enough from the news articles without having to go to the paper.
Okay.
You know what I mean?
Yeah. Well,
Thus rendering this episode worthless, but
it was a fascinating discussion. I learned so much. Constants aren't constant.
good. I feel like an hour just literally disappeared from my life. I feel like we were just talking about Twitter and Instagram.
Well, fortunately, time is relative. Universe is expanding. And
This is a circumnuclear episode.
what's time anyways, man?
Yeah, hits joint.
All right. Thank you, everyone, for listening and tuning in again. Hopefully, we didn't blow your minds too much with this episode. But if we did blow your minds in a positive way, and you want to check out our website for more details, we will post the news articles and the journal paper as well from Nature if you want to check it out. Also, if you have any thoughts, comments, questions, concerns, existential problems in your life that you think science might help with, feel free to hit us up on social media or email paperboyspod on Twitter and Instagram, paperboyspodcast@gmail.com.
No, paperboyspod@gmail.com.
Paperboyspod. It's Paperboyspod everywhere.
Except for the website, paperboyspodcast.com.
This article blew my mind, man.
Yes, it's highly confusing now.
Can't even mind my P's and Q's.
We're also on Patreon, like we mentioned at the start. Patreon.com/paperboyspod. Please just go check that out. James and I love doing this show. We're already swimming in cash from our grad school stipends, but just a little bit of support for the show goes a really long way to helping us make the content really good and improving our equipment and being able to do more bonus episodes and start doing videos. Just there's a lot of stuff we want to do with this show that just a small little boost each month would help us to expand. So
Yeah, makes it exciting for us to know people are listening and appreciating, and gives us motivation to add more. Like, we added a YouTube channel, so we'll start filming live videos as well, and some additional content.
yeah, and it's kind of like it's just a great way for us to commune with listeners. Like the people who are on our Patreon, I think have like a level of access that you really just don't get if you're just tuning in to the regular show. So yeah, check that out. Patreon.com/paperboyspod.
Thanks so much for listening, and please join us next week for another exciting edition of Paper Boys.
Thanks for listening.